We're going to get started here. Today's discussion is going to be about scheduling. So I'd like to start the discussion today by talking a little bit about the linkage between scheduling and estimation, which is the last topic that we covered. This is non-functional. Let's try that again. So today's topic is scheduling, and I'd like to begin by linking this to the last topic we discussed, which focused on estimation. So, using techniques of estimation, such as the decomposition-based methodology, we could take our project and let's suppose the amount of work that's required for a given incremental deliverable, and we could divide it into a set of tasks, which for the sake of estimation, we might further subdivide into sub-tasks, or small concrete pieces. So we can have maybe task 1, task 2, 2, 3, 4, etc. Maybe these are various tasks that need to be acted on to deliver the anticipated functionality for a given deliverable. And what did estimation give us for each of these tasks? What came out of estimation? The methodology we talked about. Was it just one number? Good. A worst and most likely, for example, and then we actually derive from that. So this is kind of the mode. We actually derive from that also a mean at one point. We could throw that in there. An expected value. Sort of the one that is sometimes different from the single most likely point. And this is maybe task name. Okay, so suppose we were to do that, and sounded like a lightsaber or something. And suppose we were to do this, and we were to take into account, suppose we have amazing precision within our estimation, and we know that if we total up all these tasks, we will... we're seeing something like 40 hours of developer time in the best case, and maybe 50 hours of developer time in the worst case. And I could fill in most likely, maybe let's say 45. And suppose we have 4 developers working on this. In terms of calendar clock hours, maybe these are days. Let's just say days. It's a long sprint, but say days. Suppose we have 4 developers. What's the minimum time in which we can deliver on this? Suppose we have 4 developers. What's the minimum time? We have 40 developer days worth of work.
10 days.
Okay, 10 days. Now, why is that a bit of a loaded question? Because the tasks depend on each other. It may be that you can't start certain of these tasks until they're finished, right? It may be that you can't do the integration testing of module A and B until modules A and B are each delivered. You could set up it in a mocking sort of way, but you can't actually do the testing. It may be that you can't do the review, the inspection of the developed code for module C until that code is developed. So there's dependencies. There's dependencies between tasks. And we can't simply naively go from a total amount of work in terms of person days or what have you, or person hours, into a amount of time because of these linkages, these dependencies, to prevent us from undertaking, for example, 2 tasks in parallel. So within the course of this lecture, we're going to be discussing this technique known as project scheduling, which is ubiquitous in the project management area, that allows turning many task durations and dependencies into estimates of project length. Provides a sort of straightforward way for taking tasks and some understanding of how they depend on one another and turning it into a length for the entire layer project, say a deliverable, a given deliverable. Now, it turns out that scheduling is very widely used not only to understand the timing, but to understand the cash flow as well. This is particularly key in other industries such as construction, which, like software, have very custom projects, but where there's a very strong attention paid to, because it's very capital intensive, and you've got to pay subcontractors and for material all through the project often. There's cash flow going out for different subcontractors doing different types of work, different trades, for example. And so scheduling in some contexts can be used together with resources representing cash flow or other scarce resources that might apply in the software area as well. For example, there are cases in the software domain, or at least the firmware domain, where specialized hardware is needed for certain types of testing. You need a logic analyzer, or you need some sort of special hardware debugger to debug certain types of firmware issues involving computer engineering components. So components with the say embedded systems to be deployed. Scheduling here is critical to understanding often the financial side together with the time value of money and discounted cash flow ideas. I don't have time to go into that here, but it's a rich and interesting topic that in past years I used to teach towards the end of this class. And if there's time allowed, I might talk about it. So why do scheduling? Well, it turns out that scheduling is a process that is very useful. Dwight Eisenhower once said, does anyone know who Dwight Eisenhower was? He's a what? That's interesting because he died before you were born, young man. But so does anyone know? He's commander of the Allied Forces in what? World War II. It was World War II. Yeah. Dwight D. Eisenhower. I think that's correct. Yeah. He also later went on to become president of the U.S. And he was a very popular leader, and there's a number of interesting quotes attributed to him. My two favorite, there's two favorite of mine, one of which is directly relevant to this. He said, "The plan is nothing, planning is everything." A previous military strategist, Clausewitz, who was in the Prussian army and a master strategist, once said that no plan survives contact with the enemy. Every plan goes out the window in the sense that it no longer plays out in exactly the way you anticipate. But thinking it through ahead of time, doing the planning, helps you identify the key issues, the things that have to be coordinated, etc. So that even if you're knocked off kilter, you can recover much more quickly. You know what has to be done and some of the order in which it has to be done. You can innovate more effectively and robustly. Scheduling lowers the chance that a delay will be experienced by a project, and it assists in recovering from any delay and resolving responsibility for where that delay came from, who might have been responsible, or what sort of process might have been responsible for it. And for larger projects, you think about something like shipping the next version of Microsoft Office, or for rolling out Eclipse, projects which have a huge number of details associated with them. You've got a very complex challenge in place to sort of making that happen in on a very clear timeline. And scheduling can be incredibly helpful to for planning these things. Scheduling plays a key role within projects, regardless of industry. It's across many industries. Scheduling plays a role in the design, figuring out milestone times for certain types of activities, times to meet, to coordinate on things. And if you're dealing with a project which involves subcontractors, as a lot of IT projects do these days, offshore contracting is quite popular. You farm out contracts overseas for certain pieces of them or to other companies. This can be really key for setting schedules for those subcontractors. But I think for the sake of this class, the key benefit that comes from this sort of scheduling is figuring out the critical path. And I'm not asking anything fancy from you in your projects, but I am asking you to think about what the critical path is. This is the set of activities, the sequence of activities that cannot be delayed without delaying the project. And by project here, I'm talking, for your sake, about an incremental deliverable. So the whole incremental deliverable will be delayed if you can't keep a certain set of activities on track, whereas other activities often have slack. They have give. They have they're a little bit looser in their timing. So being clear about what's on the critical path and what's not can be really helpful for delivering successfully and on time. It does provide a framework for monitoring, for cluing us in what things need to be monitored most closely, and as I mentioned, understanding cash flow over time. I think I'll skip forward on this. I should note that scheduling is not ubiquitously required or advised. So there's a certain amount of activities that we don't schedule, particularly for software, but also for other domains. Fundamentally, scheduling does have an overhead associated with it, and it's an overhead of formulating it, putting it into software, working with it formally, updating it if you're thrown off schedule. So typically we don't schedule minor activities like these various sub-tasks within tasks. And we will often not schedule things like who does an informal peer review. We may not schedule certain types of debugging activities because we don't know whether or not they will be needed or how long they'll take. And often in software development, who exactly is doing what is sort of the coding pipeline to keep busy is often not scheduled out ahead of time. It's not scheduled statically. It's scheduled dynamically. It's kind of first come, first serve. Someone's ready for another task, they can take it on. So there's many things we don't schedule, but broad tasks, I'm talking here on a per incremental deliverable basis of maybe 3 to 6 tasks that will typically form major components of a given deliverable. You might want to really think about putting those in an order in terms of dependencies to make sure the tasks that need to start soon, because they're on the critical path, get going soon. So you're not left hanging towards the end of the incremental deliverable. So there are some things we don't schedule, but I am looking for you to schedule something. Now, the most classic form of schedule is this. It's called the Gantt chart. How many people have seen this before? Gantt charts. Okay. If you go to project management offices worldwide, again, regardless of industry, when I come and visit some of you folks in your internships next year, there's a pretty good chance that I'll see this on the wall of some manager's office. What does it represent?
The tasks, the order, when they're starting, when they're finishing.
Great. Tasks, their order, when they're starting and when they're finishing. So let's unpack that. Where are the tasks listed here? This is a two-dimensional graph. Where are those tasks listed?
Along the y-axis.
Y-axis here, yeah. So here we have, certain tasks that have to be undertaken, and where's the time? Left and right, yeah. And we'll see that continues all through today in our diagrammatic representations. Now, each task is associated with either an event, as shown as sort of being a simple triangle, or a defined duration here, shown as a line. So here, a line between weeks 3 and 7, or 3 and 6, for example, indicating a certain amount of time at which cost data is being submitted from functional units or what have you. So this kind of maps out a project and its progression over time, and gives you a sense of kind of what's going first and what's going later. What is it missing from the standpoint of what we've been talking about? What is this missing? So it maps out what's being done when on your project. That's pretty good. What is it missing? Dependencies. It doesn't tell you, okay, if you're delayed, for example, in this distribution of schedules and work breakdown schedule, how does that push things back, right?
It can, though.
It could. You could put lines between things, and there's a variant of that. Sorry?
You could have it in paragraphs. So everything that starts at a certain point.
Yeah.
The next 3 down, for example, you have a horizontal line saying the next 3 down all depend on this. This is that.
Yes. Yes. So as I said, you can elaborate it graphically, and you'll see this sometimes with lines between tasks that show dependencies. But in the classic form of Gantt charts, that's absent. Gantt charts originated in World War I, and they were a very effective communication tool for kind of mapping out the planned sequence, but they traditionally did not have ways of indicating dependencies. And modern softwares elaborated them, drawing on this approach we'll be talking about of CPM scheduling. This elaborated them with dependencies. So here's another example of a Gantt chart. And you can have sort of hierarchies of Gantt charts that break them up into pieces. So Gantt charts are great. They're fantastic ways of summarizing plans for a schedule. So you could imagine that Gantt chart type of mechanism, for your project, for your incremental deliverable, week 1, week 2, maybe broken down to successive days, who's doing what roughly. This is the day where Anam is back. This is the day where we're going to have this inspection. This is the day where this thing has to be done to be ready for the inspection. You can map that out and have some sense about, okay, are we behind? Are we on schedule? Are we progressing as anticipated, or are we in for a hard landing when it comes to the incremental deliverable? Schedules can give you that sort of information. Now, the next major advance in scheduling historically has been the introduction of the critical path method, which lies over 50 years in the past now. This, by contrast, was created in an industrial context, not for a war effort. It's gone through a variety of kind of adaptations and variations. And you'll see it in all sorts of different modes. And I'll try to give you a brief glimpse of a couple of them. But the idea here is that you diagram out in a directed acyclic graph. What do I mean by that? How many people have heard that term before? A DAG. A DAG? Yeah, okay. So what is a DAG? Okay, it's a directed acyclic graph. Okay, are trees DAGs? Is every DAG a tree? Give me a DAG that's not a tree. So here we have, say, A. Here we have B and C. Is this a tree? Yes. Although to our friends in the forestry area, they might not recognize it as such. Okay. You could have B going to C. Okay. So if you had these sort of dependencies, yep, you bet you could. Or you could have a D and both B and C go to D, right? You could have this sort of triangle. So those would be legitimate DAGs, but not trees, right? And in general, these sort of diagrams can be described as DAGs. And two of the popular ones historically have been those that are called arrow networks and bubble networks. And an arrow network, the tasks over here on the right, the tasks are actually shown as associated with the arrows, and on the left, the tasks are associated with the vertices. The arrows indicate dependencies. By contrast, on the right, the arrows are the tasks, and the nodes indicate sort of momentary instants that are associated with certain dependencies. So we're going to be talking about this form, which is within recent decades become the dominant form. So I'm going to be discussing a simple algorithm that's going to be involved in performing scheduling from a set of durations, so tasks, each associated with durations and dependencies. So there's a set of activities determined from a task list. You estimate the duration of these activities, and in some versions of this, you further indicate resources, including dollars, associated with them, and then you define the dependencies between the activities. And basically what you do then is you perform a scheduling algorithm, which is a simple order n algorithm. So its running time goes up linearly with the number of tasks that are associated with this particular problem. Now, normally this is, and particularly in some industries, this is done in a very cyclic way. So from the schedule, you estimate time, cost, and resource use, and if it's acceptable, you terminate. If it's not acceptable, you further refine your dependencies. So to make sure, for example, that you're not requiring two of a given resource, of which you only have one at the same time. So if you only have one in a construction project, if you have only one dozer, and your CPM schedule has the two dozers in use at the same time, you impose a dependency so that they're not in use at the same time. We're going to be simply dealing with this with a simple CPM schedule, single pass. Okay. Now, key to this is mapping out tasks and their dependencies. And often in modern software, these tasks are illustrated with rectangles, and we're drawing dependencies illustrated as arrows. Now, it turns out that these arrows encode different types of dependency, different types of constraints. Some of these constraints are logical information constraints. So you cannot have the inspection of product A until A is developed, and potentially what you'll even have is, A goes through a debugging phase, perhaps, and so you have A developed, and then A can't be debugged until it's developed, and A can't be inspected until both the debugging and development are done. So here we have sort of a logical information dependency. This inspection depends on information from these earlier phases. In other cases, these dependencies can be managerial. They can be based on regulatory rules. You cannot put your system into operation until it's gone through a set of validation or acceptance tests. So for certain subdomains of IT in which I've worked before, such as pharmaceutical companies, there's a very rigid process of you have to go through gating phases, and you're simply not allowed to put a system into use until it's gone through certain gating phases. So it's perfectly ready. From an informational standpoint, it's all there. From an accessibility standpoint, it may be there, but from a standpoint of being allowed to proceed, it's not there. In some cases, there may be physical dependencies. So perhaps, for example, there's a usability space where they study a person's interaction with the product, and there's only one such space. that's built for sort of observation of this at a time, so you can only schedule one person at a time. So we're going to be talking here about activity on node representations, where these activities are associated with these nodes on the graph, and where these arrows are associated with dependencies. Okay. Now, these dependencies, if you go to professional project management software, things like Microsoft Project or Primavera Project Planner, which is an extremely popular product, you'll find that these types of arrows come in a variety of flavors. And we won't be talking about the nuances of this. I used to, but no longer. But the type that we'll be assuming here is what's called a finish to start activity. And what I mean by that is that the preceding activity has to finish before this next activity has to start, or can start. Okay? So this activity, inspection bay, can't start until A's debugging is done. And that's a very, very common one, and certainly the most common one in applying these. But you'll find that software out there supports a variety of other types, start to start. This activity can't start until this other activity starts. Maybe my pair programming with you can't start until, you start developing this code. There can be finish-to-finish ones. This one can't finish until this other one finishes up. And so, for example, debugging may not be able to finish until the testing is complete, etc. So you should be aware that we're presenting an extremely simplified version of these sort of activities. Now, what we're going to get out of the scheduling algorithm is listed here, these 4 items here, okay? We're going to get out, for each of these tasks, 4 things, and sometimes they're put in the 4 corners. So one is early start time, okay? The early start time. And what this means is sort of the soonest that it could start, given all the activities that have to be finished before it. Another is the late start time. Now, late start is the latest that this could finish, the latest it could start and not delay the entire project. Okay? So we have early start, late start, and then we have early finish and late finish, which are corresponding values for the finish. And for our cases, finish of that activity. For our case, the early start and the early finish are going to be trivially related to one another, by the early finish just being the duration of the activity plus the early start. So if we have the early start and the late start, we know by just adding the durations that we can get the early finish and the late finish times. Okay, so all we do for our case is add the duration of the activity. So it's particularly trivial. This is not in general true, particularly where you have different start to finish to finish, start to finish types of dependencies. So in general, we're going to have this very simplifying case. So for example, we might have here a diagram. We have a start, and we need to start developing the system. We need to start internationalizing the system. What do I mean by internationalizing it? This is a term that first came up in spades in the 80s in software, in the commercial software business. But it's now kind of an incredibly central part of a lot of software development projects.
Language?
Yeah, it's language. It's making with the help system as well, and then you'll finish up. A key thing here is that you are often keenly interested in when's the earliest time you can finish the entire set. And hence this focus on kind of late start, for example. You're wondering, what's the earliest we can finish this whole project given what we have to do? And you want to keep your eye on that ball. You don't want to leave anything to chance in terms of letting the project unnecessarily be pushed forward. If you can finish this thing in 2 weeks, you want to keep your eye on what you need to get done in those 2 weeks so that you can deliver on time. And the fact of the matter is, per my comments on critical path, and we'll see this, that certain of these things will be on the critical path and certain not. So certain things you need to watch very, very closely, and certain things you don't have to watch because we have some lead time with them. We have some slack. Okay. Okay. So I'm not gonna go over activity on arrow here. Let's talk about the CPM algorithm. It's a very straightforward algorithm. I would argue that you've applied in a certain form pieces of this algorithm in your daily life since when you were considerably younger than you are. For the past probably 10 years or so. It's based on a familiar set of intuitions and a familiar set of sort of ideas and constraints. So what does this take in? We'll explore that in a minute. What does this take in? It takes in tasks, such as names associated with them, their durations, and their dependencies. These are directed dependencies. A depends on B, for example. And what does it put out? So that's its input. What are its outputs? Well, its outputs are these things I've drawn up here on the board. These 4 things here. Early start, early finish, late finish. For each task, we provide this, okay? And it's linear time in the number of tasks, okay? So we're going to cut off the sort of time mentions here, just in terms of how we describe these things. And we're going to refer to these as early start, late start, early finish, late finish. Okay, and I've mentioned these. I want to highlight late start and late finish are not the latest that they can start, having kept busy with other activities. These are the latest that they could start or finish. Late start and late finish, the earlier a task could start or finish without delaying the entire project unnecessarily. That's the whole point. You don't want to delay things unnecessarily. You want to let this project come in on the minimal time that it could take. You don't want to squander that unnecessarily. Okay, so we're going to associate diagrammatically this type of information with tasks here within this framework here. So we're going to have and maybe I'll do it over on this board. This is the most expendable. We're going to actually put up a diagram, and you folks are going to run the algorithm. Okay? You're going to run the algorithm for me. So the diagrammatic convention we're going to use is as follows. It's shown up here in the upper right. And this is one of many. I've shown some others down here to the lower right. There's one on the previous slide. So what we're going to do is we're going to divide up each task is going to be denoted with a circle here, and we're going to divide this up into pieces. So this top one is just going to be sort of the number of the task. The bottom is going to be the duration in hours or duration in days. So maybe this is 2 days. It's task 1, or it could just as easily be task A. This is just a unique categorical denotation. And we're going to have early start up here in the upper left. And then we're going to have early finish up here in the upper right. Okay. Early finish. Again, could you remind me, what is early start?
The earliest that it can start based on the previous task.
Yeah, based on the activities that have to precede it. Good. So based on those dependencies. And then down at the bottom, we're going to have late start. What is that?
Latest that it can start without watching the project.
Yes, good, good. Okay, and then late finish. Okay, so we're going to associate with each activity those quantities, and I'm going to come back to this notion of float, slack, give associated with activities by just noting it's the difference in the late start and the early start. If this is the earliest you can start it, and late start is the earliest you must, by the time the latest time you must start it in order to finish it on time, you actually have some latitude, you have some give, you have some slack, you have some float in terms of when you start it. You could start it as early as the early start. Can't start it before then. Why? The other stuff hasn't been finished. And you have the luxury of finishing it as late or starting it as late as late start without adverse impact on when the project finishes. You can delay up to here for free, so to speak, without delaying the entire project because it's waiting for something else. Have you folks taken, how many folks in here have taken chemistry? Good. Hey, great. So did they talk about the notion of a rate limiting step in chemistry? Yeah. Okay, so in a way, it's a similar concept. The bottleneck fly elsewhere in a project. And so certain tasks might be delayed comfortably because you're waiting on something else. It's not going to be delaying it. And we'll see this is a very familiar notation, a very familiar notion from daily life. Okay, so let's talk about this algorithm itself, and then we'll unpack it to very familiar things. So basically, in this algorithm, we're going to set the early start for each starting node to some reference value. And for the sake of this, we're going to start to day 0, okay? We're not going to make it March 6th or something like that, some real-world date, although we could just as well. We're just going to refer to it without lots of generality as day or time 0. And we're going to go through 2 passes. One will be a forward pass. It's going to take O of n time. We're going to go through each task in turn. And one will be a backwards pass, okay? And each of these will have some logic associated with it. Each of them is going to have some logic. And the key things I'm going to highlight here are the fact that they differ in 2 major things. So if we consider the forward pass and the backwards pass, I guess I should really say 3 things. First of all, they differ in the order, whether they're going forward or backward. That's indicated by their name, and it's pretty obvious. A second thing in which they differ is when you're deciding a value for a given node, whether you're deciding the finish time for that node, late finish, for example, or whether you're talking about the start. The start time is sort of the thing that's being computed. And what you're actually doing here is to compute that, you're considering certain information. In the forward pass, you're considering the information from nodes you've already covered, and so it is in the backwards pass. But in the forward pass, the things you're considering are from nodes earlier in time. In the backwards pass, it's from nodes later in time, your successors, okay? And finally, and this will be key as you do this on the exam, it's this notion of are you taking a maximum or a minimum here, okay? And we're going to see that this unpacks in a familiar way. In the forward pass, you're taking a maximum of the early finishes all of the things in which you depend have to be finished before you can start. Can't start till each and every one of the things that you're depending on is finished. Forgive the English. And then in the backwards pass, you're trying to figure out the late finish. And the late finish is the latest you can finish without delaying the project is dictated by the minimum of the late starts of the things that depend on you. If there's something that has to finish, it's something that depends on you that has to finish by a given time, a quite early time, you have to finish prior to that. So, if there's something that depends on you that has to start by a certain early time, you have to finish at least by that time. Okay, so here's the intuition behind this to sort of unpack this into very familiar terms. Okay, so it's 8 a.m. on a Saturday morning. ID 4 is due any day now. This is the scenario that's not in reality. And it's 8 a.m. on this morning, and you want to know the earliest time you can arrange to meet your team after you do some tasks at home. And so here you have some things which you got to get done before you can meet your team. You need to take a shower, which will be very speedy, 5 minutes. You need to boil some water in a water heater for breakfast for 10 minutes. You need to eat breakfast, which is going to take 15 minutes, and then you got to walk to campus in 20 minutes. What's the earliest time you can meet your team? Okay, so
you eat breakfast in the shower.
Okay.
You boil the water while you're showering, you eat breakfast while you're walking to campus, and then you should be done in 35. What kind of boil water thing is take 10 minutes? You can donkey shower. Have a hot shower, then you can skip that. If you have a hot shower, you fill up.
Okay, so what are you doing in your head? Just reflect on what you're trying to do. Besides, yes, you're trying to figure out what things can be done in parallel, and you're trying to figure out how long it will take for the entire thing by breaking it into pieces. Now, what things can be done in parallel and what things cannot are key to this. So taking a shower could plausibly be done in parallel to what? Boiling water. Probably not to walking to campus, but or eating breakfast. That's interesting. Yeah, that's true. If it's raining. Okay. Enough comments from the peanut gallery here. Okay, so you can take the shower and boil the water at the same time, but can you start to eat? When can you start to eat breakfast? After you're done both of those, right? And you can't start that until the maximum of these times are finished, right? You're constrained by boiling the water. You could take a super fast shower, or you could dawdle in the shower. But the thing that's probably going to be the big constraint here is boiling the water. So you have time actually to use a bit more soap, lather up a little bit more with your hair, and still not delay your breakfast, eating your breakfast, right? That's the critical path here is boiling the water up to this point. Then you can eat breakfast and you can walk to campus, okay? Now, arguably, you can eat breakfast while walking to campus. The claim was that at MIT, you couldn't be a student until you could eat and walk at the same time, and to be a faculty member, you had to be able to run and walk at the same run and eat at the same time. And I've seen illustrations of that. So here, you could in principle try to parallelize these, but what's going to be the critical path then? If you were to parallelize eating breakfast and walking to campus, so you're eating your oatmeal while you're walking. What's that? Walking to campus is going to be on the critical path. So
The problem with that is if you try to parallelize that,
yeah, it will take longer. Yeah, that's true. Except if you're eating like pizza.
What
It's not that, well, okay. Anyway, we won't.
Yeah, I'm not trying to say that from a perspective of it.
No, it's, no, you're absolutely right that you're, I think what you're highlighting very helpfully, and perhaps this was your sage intention, was to highlight the fact that we make abstractions about things that eating breakfast will take, X time, and that's a simplification. The simplification breaks down in some cases. So if we're running, it may take us longer to finish our oatmeal or not. Yeah, in terms of, so it's an abstraction. Okay, the point here though that I want to emphasize is in figuring this out, like when you can start eating breakfast, you're taking the maximum of these times and figuring out how soon you could get to campus if you're eating at the same time as you're walking. You're considering the maximum of these two times as being sort of the limiting factor about when you'll be presentable to your team, right? Okay, so now let's do a backwards pass. That's the forward pass. I mean, that was basically, we did a forward pass on that. We were considering how quickly we could get there. Let's do the backward pass now. Okay, so you have a plane that leaves for Australia at, well, okay, it leaves at 12 p.m., okay? You want to know what time you have to get up to make the plane. What do you need to do? You need to take a shower, boil water, eat breakfast, call and wait for a cab, take a cab to the airport, check in, and you need to sit on the plane before takeoff for at least 20 minutes. So for what? For what time should you set the alarm?
Well, the last three steps you can't parallelize all.
Well, okay. Check in manually. You've got a big bag, okay?
I'm talking about the confirmation part of check-in. If you have a checked bag, it's terrible, but if you have the area, you can do it all in separate tabs.
That's true. Let's assume that. Okay, well, fair enough. But let's assume that those are in parallel. Then what are we doing? What are we?
You could call for the cab while eating breakfast.
Good. Yeah.
You eat breakfast in the cab. That's not really hard.
Okay. So if you want us to think this back, okay. So noon, you've got to be at the gate, ready to board the plane by what time? 11:40. Okay. You have to check in therefore by 11:20. You have to get the cab to the airport. If you're sure that the cabbie is your brother and they're going to get you on time, you're gonna need to have the cab pick you up at. Okay, this is not recommended. Okay, I do not recommend this. This came close to happening on Monday, and it was successful, but I would not recommend it to anyone. Okay, when do you have to call and wait for the cab?
In the middle of your boiling water. No, before you get in the shower, actually. Before you get in the shower.
Yeah, you can do it before you get in the shower, actually.
Breakfast in the cab. Yeah.
Okay.
And you boil water and wait for the cab while in the shower. But if you need to boil water, you're probably eating oatmeal, but nothing else. Yeah. So what you have disposable and food.
Okay, so when we have activities in parallel, if we're, for example, eating breakfast and waiting for the cab, if we have to call and wait for cab started by a certain time, and we have to get eating breakfast started by a certain time, the latest we could finish the boiling of the water is what? It's associated with the minimum, it turns out, of those two. Those things each have to be started, so if those things depend on a previous task, maybe taking a shower is a better example. Taking a shower, then the latest you could finish taking the shower, not delay the whole thing, is the minimum of the latest time you could start taking the breakfast, eating your breakfast and waiting for the cab, that you could start then. So let's go talk about a practical example of this, and we'll actually diagram it up. So So we're going to have a, here we are. We've unpacked these tasks into a set of activities, and I'd like you to help me draw this out on the board so I don't have to crane my neck too badly. So we've got number 1, 2, what's this next one? 2, 7, okay, 2 and 7. So what is 7 indicating here? Days of duration, yeah. Okay, next one down here. 3 and 2, okay, next one. 4 and 2, next one. Okay, 7 and 6, and then we have an end sort of dummy node that sort of represents the end. Now there's a branch off from 2, 7 here, right? Okay, and this guy is what, 5 and 4? Yeah? And how about the next one here? 6, 4, okay, and then he merges in at the end. Okay, great. So you're going to help me run the forward pass and the backward pass up this. You'll notice that these things have names associated with them, but mathematically we can boil it down to applying this algorithm. So, ladies and gentlemen, remember this notation here. Early start on the upper left, early finish on the upper right, late start on the lower left, late finish on the lower right. Okay, so we're going to, without loss of generality, call the earliest start of this first task day 0, okay? What's the earliest it could finish? 2, time 2. It takes 2 time, and there's no way it could finish before that time is the abstraction. Okay, what's the earliest this next task could start? 2. Yeah. Why is that? Yeah, it depends on finishing. Remember, this is a finish to start dependency. It depends on finishing this previous task. It can't proceed until the previous task number 1, is finished. So it's associated with an early start time, this time before which it can't possibly start because the preceding things haven't finished up, of 2, okay? What's the earliest that it could finish? This is a 7 at the bottom. 9, good. Okay, next task here to the right. What's the earliest it could start? 9, finish. 11, next start. 11, 13, pretty good. Yeah, and the next one? 13, yeah, and 19, good. Great. Okay. Now let's go down to complete this first pass, this forward pass. Let's go down to this next one. So this is, now we're in the lower one here, task number 5. What's the earliest it could start? 9 as well. Okay. It can be going on in parallel with task 3, right? And for that matter, task 4, task 7, yes, task 7. What's the earliest it could finish? 13. Good. What's the earliest this next task could start? 13 and finish? Good. Great. Okay. Now, what is the earliest the entire project then can finish? 19. Why not 17? Yeah, so 17 could finish up early, but we're depending on the critical path, the thing that takes the longest. That's 19. We can't finish the whole project until everything's done. So we can't finish the whole project until this top one is done. So that's great. So, ladies and gentlemen, recall in the backwards pass, what things are we filling in? Late start and late finish. So we're going to go back now and fill those in. So for this task number 7, what is its late finish? Good. That's the latest. That's the earliest time that it could finish. Excuse me. The latest time it could finish without delaying the whole project. Yes. So it's 19, and what's therefore the late start of it. 13, good. How about the next one, late finish? Okay, it's the same all the way back. Now, why is it the same all the way back? It's the critical path. Okay, now, can we fill in this one right now? This one with the branch? No, we can't. Why? What does it depend on also? The other path. After all, it could be that it's constrained by this other path, in theory. Okay? In this particular case, not, because the critical path is at the top. Okay, so let's fill in this next one. So this task number 6 down here on the lower right, what is the latest finish for that? 19. And therefore, what's the latest start? 15. What does it mean that these two are different, 17 and 19? Yeah, you have a two-day buffer of butter zone. Yeah, I like that. You slack, leeway, give. You have float. You have butter zone. You have a buffer. You have a safety buffer. Okay, how about this next one though, to the left of it? When is the latest that this one could finish without delaying the whole project? 15. Yeah, good. And what's the latest it could start without delaying the project? Good. Okay, so task number 2. The chickens have come home to roost. What is the latest that it could finish without delaying the whole project? 9 is right. Yeah, why not 11? Let's suppose we made it 11. What bad things would happen? We'd delay the critical path. If we said, we could wait until no sweat, we can lay back and relax on number 2 and not finish it till 11, then we'd be in a bad way because it's going to delay what? 3. And that's going to delay what? 4. And that's going to delay 7, and that's going to delay the whole project, right? So here, this node is also on the critical path. And what's the earliest, or what's the latest it could start? 2. And this first node, what's the latest it could finish without delaying the whole project? 2 and 0. Okay, so those nodes which are associated with equal late finish and early finish, late start and early start are said to have 0 float, 0 slack, 0 give, 0 butter zone, 0 buffer. I like it. Can we put that on final? Yeah, butter zone? Sure. I'll take that in. I'll give partial credit if it's margarine zone. Or ghee zone would also be acceptable. Okay, so here we have this path, which is path going from start to finish. It's the longest path, which is the critical path. And there's no give to that. If you slack off on task 1, 2, 3, 4, 7, you're going to delay the project. That's it. Now, meanwhile, this lower path, you could burn 2 days, and when you start task number 5, and it's still going to be okay. You could start it as early as 9. It's ready to start, but you could start it at 11 and still finish in time. Does that make sense? Yes, Alex. Yeah, you can set it to have multiple finishes if you want to, although that would be a little bit. Exactly. Yeah, so you could declare this as a node which has its own sort of components. The key thing is that you don't, what you're trying to avoid is unnecessarily, gratuitously extending the time of the project through sloppiness, right? Yeah. You can have multiple critical paths. There are cases. It's comparatively rare. What's more common is you have a shifting critical path. So what happens, and this relates to Kurt's the Krugerian wisdom dispensed earlier, that sometimes the actual durations are different than what you anticipate. And so what would happen, for example, here, ladies and gentlemen, if this task, number 5, that you thought would take 4 days actually ended up taking 8? Where would the critical path be then? It would be on the bottom. It wouldn't be on the top. So what's quite common is that you have a shifting critical path. And this is one of the jobs of the project manager, is to kind of keep track of, okay, where is the critical path at, and are we forming a new critical path so that we got to ride that one really carefully. The critical path is the one that you got to stay on top of. It's the one you got to make sure that things are getting done on time, because if they ain't, it's delaying that project. And if something ends up taking a lot longer than expected, like node 5 here, you could find that now you've got to really pay attention to node 6. And that if you take your eye off the ball with node 6, you are going to be delaying that whole project. Does that make sense? Yeah. So yes, you can have multiple critical paths in principle. There are cases where it occurs, but it's kind of based on this race condition, as it were, that this path and that path will finish at exactly the same time. And normally, just because of the vagaries, the uncertainties associated with things, it doesn't happen that way. But what's much more common is you get a shifting critical path because things turn out differently than you thought. Or it turns out there's a dependency between things you didn't anticipate because node 6 ends up needing something from node 3 or something like that. Or vice versa. Node 4 from node 6. Okay, so the algorithm is comparatively simple. I want to emphasize what we did here at 2 key points. Number 1, at this join point here, we took the maximum of the early finish times of the 2 things that fed into it. And in general, when you have 2 paths coming together, a merge point, a join point, you're going to be taking the maximum of the early finishes of the things that come together there to get the early start of that sort of resulting node. By contrast, and that's the same algorithm we use in figuring out when we're able to get to work on time. Okay, can't start breakfast until we're done showering and we finish boiling the water. It's the maximum of those times. Going back the other way, the reverse way, we're actually taking what? What were we taking here for this late finish time of node 2? We were taking the minimum of the late start times of the 2 nodes that depend on that, to wit, task 3 and task 5. We are looking at the minimum of those times, and we took the minimum, therefore, of 9 and 11 here, and we got 9. Why? Because if there's one of these tasks that depends on us, that has to start by a certain time to finish the project on time, we need to get our house in order so that we can finish ourselves by that minimum time. We've got to finish up by that, whatever the earliest time is that one of those things is depending on to finish the whole project on time. So this is the minimum coming back the other way. So maximum forward pass, minimum previous pass. On the forward pass, it's maximum of the late the early finish times of the predecessors, and the backwards pass, it's minimum of the late start times of the successors. Does that make sense? Good. Wasn't quite all one voice, but it was an approximation. Okay, so we're finishing. We perform these two passes in order to arrive at the estimate for the whole project. Okay, so this notion of slack, of float, is quite central to scheduling. It's really the difference between when we have to finish an activity and the earliest that we could start it. And it relates to how much give we have. So, here we are, with certain tasks, we have some luxury of choice, and other tasks we don't. The critical path is the longest zero float path, okay? For the algorithm that's described, there's at least one of them. And, it needs to be completed on time or the entire project is delayed. It determines the minimum time for this project. Typically evolves over time, as I noted, and there's no flexibility to sort of delay things. Now, I should note, and do I have okay. I should note that there's generalized notions of float, and we're going to have to finish with this. What we've been talking about is total float. There's more refined notions of free float and independent float. One of the issues here that's of big practical concerns in some projects is that when we talk about float as the leeway you have, or the give that you have, the slack time that you have, it's ignoring something that's very important in some projects, which is if you are working, say, on task 5 and someone else is working on task 6 here. Task 6 depends on task 5, and the person who's responsible for task 5 eats their float. If they eat all their float, where does that leave task 6? It's on the critical path. You have pushed onto that person a great deal of responsibility, so that, they got to keep on it, or they're going to delay the whole project. And you potentially expose them to liability. You potentially expose them to being blamed if the project is delayed, just because you've chosen to kind of delay your when you finish things. So there's these refinements to notions of float that basically refine the notion so that you can have certain float without delaying any of your successors, for example. It doesn't affect things downstream, and then you can't be blamed for eating it. I won't be going into that, but you should be aware that it is used in certain areas. Okay, that's all we have time for today. Thanks very much, and I know a couple of you wanted to talk with me after class, so I'm glad to do that.